So with Alison McDonald, who is also on the US Clive Post panel, we've been organizing this series to address topics of interest to the panel. So today we're very happy to have Pierre Dutrieux from Columbia University. Pierre obtained his PhD from the University of Hawaii in 2009, working with Eric Fehring on the tropical Western Pacific. His interests, I won't say, have then migrated towards higher latitudes as he joined the Polar Oceans program at the British Antarctic Survey for a number of years, first as a postdoc, then as a research scientist. He then went on to the Applied Physics Laboratory at the University of Washington as a principal oceanographer for a couple of years until he joined in 2016 the Lamont Doherty Earth Observatory of Columbia University as an assistant research professor. So as such, Pierre has been working on the topics, I believe, of polar oceans for close to a decade now, starting up by participating in the first successful autonomous underwater vehicle operations on the Pine Island ice shelf in West Antarctica. And since he's been leading or collaborating on 4 other successful launches of autonomous ocean platforms of various types under the Antarctic glacial ice. So I believe that Pierre's expertise is particularly relevant for one of the priorities of the US Clive Post panel. One of those priorities is to coordinate efforts for addressing grand challenges in climate science, and we believe one of those is the large-scale connections between high latitudes and lower latitudes. So as such, we are delighted to hear from Pierre today, who will speak about ice sheet-ocean interaction, processes linking the tropics to Antarctic glacial ice drawdown, and the advent of robotic exploration. Thank you, Pierre. Go ahead.
Thank you very much. Thank you very much for the invitation. I certainly hope that this talk will be informative and useful to the panel and to everyone listening online. So, as Shane said, I've been working on this topic of ice sheet ocean interactions for about a decade, and I initially started working in the tropics, then worked in the polar seas, and found a way to join the two. And so I've been trying to draw those links during the talk. So why being interested in ice sheet ocean interactions? It's always useful to do introductions and motivations. So as you probably all know, the ice sheets are these big mountains, multi-kilometers thick piles of ice that viscously flow downhill towards the ocean. And so this is here a map of Antarctica, and this ice flows and then form rivers of ice called ice streams, and then these ice streams end up into floating ice shelves that form the extension of the ice sheet over the ocean, and that's where the ice and the ocean and the atmosphere interact. And these ice shelves have a key impact on the flow of ice going into the ocean, because they are the last buttressing effect on the flow of ice. So if you remove the ice shelves, if you weaken them, then you remove this buttressing and you allow for faster flow of ice on land going into the ocean. And so over the past decades, what we've seen is an increased contribution of the Antarctic ice, an imbalance, if you will, of Antarctic ice going into the ocean, contributing to about 10% to global sea level rise right now. It's a very heterogeneous pattern of contribution, but most of it is actually coming from this part of Antarctica, which is losing ice, and where the glaciers have been accelerating over the last 40 years. And so to try to understand how that works, satellites have been used, and we can look at the surface of the ice, see how it moves in time. And here this figure shows in color the areas in red are all of the ice shelves that have been thinning extensively over the last 25 years, and the areas that are blue are the areas that have been thickening. So you can see that most of the areas have either been thickening or been marginally thinning, and this area is really the area where all of the ice shelves have been thinning. That's the area where we've seen the ice flow accelerating over this time period. And now if we go to what does the ocean look like, into the circum-Antarctic, close to the ice shelf, so very close to where it's supposed to meet the ice. Here I'm showing the temperature on the seabed all along the continental margins of the Antarctic. And what you can see is the temperature is close to the in-situ freezing point, about -2 degrees C, about everywhere except in this West Antarctic coastline. So we have this strong correlation, spatial correlation between where we see warm water and where we see the ice shelves thinning and the ice accelerating. So if we zoom in into this particular area, has been contributing to global sea level rise significantly. Is it working? Is it not? I don't know. There you go. So here I'm now showing a climatology of surface of near seabed temperature. This is the Antarctic, and the shaded grays are the ice shelves in this sector of Antarctica. This is the Amundsen Sea, and the color here is showing the bottom temperature. And at mid depths all around Antarctica, there's a water mass, circumpolar deep water, that's about 2.5 degrees C. And only on certain sectors of Antarctica is this water able to creep in and follow a series of glacially carved troughs to reach the ice, and to a big or a lesser extent. And so here in the Amundsen Sea we have two critical sectors. We have the eastern Amundsen Sea, which is filled in with water on average of about 1.2 degrees C. And on the western sector, we have water that's able to get too close to the ice. That's about 0.5 degrees C, 0.6 degrees C. So if I take a section going from the open ocean all the way to beneath the ice shelf, what I have is this section from the open ocean all the way to beneath the ice shelf, and that's Pine Island ice shelf. And so what you see is indeed this warm layer water. It's warm and salty, and it's overlaid by the water that's interacting with the atmosphere, and it's created by brine rejection and sea ice interaction as well. And this water is much colder and fresher. Okay, so this is the available heat content. It's warm. It can melt the ice. But what we've seen has been an acceleration of the ice flow. And so why, has this background always been in place or not? Well, if you look at what's been going on in terms of temporal variability, this ocean heat content actually has varied a lot over the observational record, which only started in 1994 in this part of the world. It's been sporadic up until the mid-2000s, and since the mid-2000s has been accelerating. So every few years we do have observation there. So here I'm showing again the map of warm deep water on the continental shelf. And in this work, what I did is I looked at 6 observations just in front of Pine Island ice shelf, which is the glacier that's been accelerating the most to date. Now there's another big contributor that everyone is targeting, which is the Thwaites Glacier just right here. And so here I'm showing profiles of temperature in this work, average just in front of the glacier, and they're color-coded by time. And so you can see that in 1994, what we had was this profile here, where we had about 1 degree C bottom temperature and a thermocline that was roughly centered around 500 meter depths. And then in 2009, we had actually a thermocline that was much shallower, much higher in the water column, about 100 meter higher. And then in 2012, we had a big drawdown of the heat available to melt the ice. Okay, so and these changes, of course, are reflected also in the salinity structure. So we have large variability of the heat content. If we go a little bit more details, how these come about, what we did is in 2009 we put a mooring in front of this particular ice shelf, and then this mooring has been replaced since continuously. So here I'm presenting a 5-year record from 2009 to 2014, January 2009 to January 2014, of the heat content from close to the bottom to about 400 meter depths. So we're cutting the top because we don't want icebergs to destroy the moorings. And what you see here is indeed a variable ocean heat content. And so between 2009 and 2011, we had a roughly continuous warm water layer at the bottom, and then this warm layer got eaten up by some processes. So if we decompose, this variability in time, that's one thing that can be done. We basically can decompose it into a slowly varying part, and then a seasonally varying part, and a residual. And so at the intra-annual timescale, what we see is that starting 2009 we had warm water, and then mid 2011 we had starting a strongly significant decrease in the oceanic heat content. At the seasonal timescale, we also have a surface expression of strong exchanges, so strong loss of heat during the later part of the year, and a gain of it during the remainder of the year. And then we also have a lot of residuals, which I won't go into today. So the basic schematic, if you will, of what our understanding up to now is the following. What we have in general is we have an ice shelf that goes, floats above the ocean, and we have this cavity where all of the exchange take place. So we have warm water sitting offshore in the Southern Ocean, and some of this warm water is able to creep in onto the shelf, melt the ice. When it does so, the resulting meltwater is buoyant because it's very fresh, and so it flows up following the ice phase and exits the ice at intermediate depths, and in this setting pretty close to the glacial bed all the way to the calving front right here. At the surface and strongly at seasonal timescale, what we have is a buoyancy forcing due to the formation and melting of the sea ice. And so at the beginning of the winter or fall, what we have is strong brine rejection, salinification of this water column. And so we have a cold, denser layer forming right in front of the ice shelf. And so that lowers the thermocline. We also have changes in the wind structure at the seasonal and intra-annual timescale now. And this change in the wind structure modifies the flow of offshore water going onto the shelf. So the mean structure is that of a volcanic shear on the continental shelf edge, where we have an Antarctic slope front, and leading to, in some cases, a strong undercurrent. So in the warm cases, and a strong undercurrent, and this undercurrent then is guided by the topography to lead to flows onto the shelf. And in other times, when the wind is unfavorable, this undercurrent is much weakened, and so this wind flow onto the shelf is weakened as well. So in this study in 2017, what we used the mooring to look at, try to quantify, which of these processes mattered most and at what time scale. And so what we did is used the surface buoyancy forcing, so the heat flux at the surface of the ocean, deduced from satellite observations. So it's not a perfect estimate, right? It's a remotely deduced estimate. And what we can concentrate on here is basically this curve going in time from 2009 to 2015. If we integrate all of the heat flux over a 400-meter water column, we obtain the red curve, and so we see this seasonally varying pattern. And then the blue one is actually the observed one, and so it reproduces well the seasonal variation and fails to mimic a little bit the intra-annual component and intra-annual modulation of this variation, probably due to feedback between intra-annual and seasonal variability. But it basically it does not really explain the intra-annual component of it. And so to look at the intra-annual component, what we need to focus on is actually the wind. This has been looked at also in multiple models, but this is observation-based talk, so I'll concentrate on the observations. And so here, basically what we had is we had a sense that the water was always warm, or the heat content was increasing over time, and that was the reason why the glacier had been increasing, because the ice shelf had been thinning, the buttressing had been reduced, and the flow of ice had been increasing. But in 2012-13, as I showed earlier, there was this big cool anomaly. And so to try to explain it, I want to look at the wind and the wind structure. Instead of being the wind flowing in this direction, which is in the climatological way, there was this huge anomaly going in the completely reverse direction. So basically completely shutting down this undercurrent shown by the arrow here that leads to inflows following the bathymetry. And so when we look at the wind, which is the red curve here, average with 12 months moving window, it's always positive, except right at this time. That's actually over 30 years reanalysis time period. That's the only time where it went negative. And so that was, the leading hypothesis was at the time, we had this very strongly negative anomaly in the wind, which shifts the undercurrent from being positive to near zero, and it shuts down the heat flux going from the open ocean to the continental shelf, leading to this cool anomaly. Now another curve that's plotted here is the green one. And the green one is very strongly correlated with the red one, and the green one is the Niño 3.4 index. So we've since dug in a little bit further on that, and there's work still going on. But the very cool thing that's basically linking the two regions, the tropical Pacific and the Amundsen Sea, is the following. Whenever there is a convective anomaly in the tropical Pacific, so basically El Niño, a movement of the convective center in the tropical Western Pacific, zonal movement, that leads to an atmospheric wave train that radiates this anomaly forward. And so here I'm showing 4 different years, but it's just the main pattern to look at is this wave propagating into the troposphere forward. And it hits the pole right exactly, of course, in the Pacific sector of Antarctica. The Amundsen Sea sits right at the center of that. And so here on this figure, what I'm showing is actually in blue is the wind. All of these time series have been smoothed with a 2-year time moving window. It doesn't really matter for the results, but it makes it cleaner. And so the blue one is the wind just in the over the Amundsen Sea continental shelf edge. It's actually this little box, tiny little box right here, green. And then the red one is the minus SOI index. The green one is the IPO index, which is similar tropical, it's a Pacific Decadal Oscillation Index. And you can see that they pretty much very nicely track one another, and the correlations are very high. And so all of these 3 panels, what they show is the correlation of the sea surface temperature in color and the sea level pressure in contour to this tiny, to the wind in this tiny little box here. So you can see a pattern that's strongly expressed and resembles very much that of the SOI or the IPO. And indeed, if I do the correlation between the SOI index and the same field, so the sea surface temperature in color and the sea level pressure in contour, I obtain exactly the same pattern, and the same is true for the IPO. So we have this very, very strong connection between the variability emanating from the tropical Pacific and this radiation all the way to the Amundsen Sea. So using this connection, what we can do is actually, here I'm plotting, so the blue line here, the dark blue line, is the zonal wind integrated over time. It's the cumulative zonal wind anomaly over this tiny region right here. And the idea here is this is the modulator for the heat content on the shelf. So the heat content on the shelf that is actually observed is shown by the little diamonds, and to some extent also by the green circles, and also by this black line. So there is not a lot of observations, but this decadal oscillation is well represented by the decadal oscillation of the zonal wind, and the red one is actually obtained by using the Niño 4 temperature and integrating the cumulative anomaly in this box as well of sea surface temperature, and obtain exactly the same pattern of decadal variability. Okay, so that's the link between the tropical Pacific and the heat content on the shelf. So the ocean heat content variability is large. Actually, the best record we have of how the heat content varies in front of an ice shelf is obtained right here in front of this ice shelf right here. So earlier I showed Banyan Glacier ice shelf. Now I'm on the Dudson ice shelf, so on the other side of the Amundsen Sea. And now we have, in this paper, we had 8 records just in front of the ice shelf. We now have 9. And so here I'm showing just 2 cases, a warm year and a cold year, just in front of the ice shelf, sections of temperature, meltwater fraction, and velocities. And so you're looking outwards from the cavity, looking outwards towards the ocean, so northward in this case. And so during 2009, we were at the peak of this decadal variability, and we had a very high heat content, very shallow thermocline. And in 2014, we were actually in the low part of this decadal variability, and so we have a much weaker heat content, a much deeper thermocline. The melt fraction is actually deduced as basically the fraction of water that originates from glacial sources. And there's water, so the circulation going into the cavity is an inflow at depths, shown by these blue areas here. So it's southward velocity inflowing towards the cavity at depths. And then at the back of the cavity, melt happens. It releases buoyant fresh water. This buoyant water then creates an upwelling, and this water flows following with the coast on its left, because we're in the southern hemisphere, and so there's an outflowing meltwater on the western side of the ice shelf. And so that's the velocity signal of this outflowing meltwater, and that's the tracer characteristics of it. So there was more meltwater outflow in 2009 when we had high heat content, weaker meltwater outflow in 2014 when we had a low heat content. We can also basically use, just come back to this, all of these sections just in front of the ice shelf and make assumptions of steady state, compute influx and outflux of heat, salt, dissolved oxygen to try to compute how much melt went on in this cavity and look at it varying over time. That's what was done in this figure, where we have temperature above freezing integrating over the entire water column and in red. And so showing the same pattern I was telling you earlier, where we have weak heat content at the beginning of 2000, and then a rising heat content 2009, and then a decreasing heat content. So that's roughly a decadal signal variability. And the meltwater flux arising from this available heat matches pretty well this decadal signal as well. There's a lot of errors, uncertainty in these estimates, but it does seem to indicate a large co-variability between the two. And the ice is actually pretty responsive to that. So during the time when we had an increase in heat content, we can see that all of the ice shelves have thinned a lot, and we can also see a response in the flow of ice and an advance and a retreat of the grounding line. So this is all determined by the ice response is very much determined by the geometry of the system, and it turns out that the Dudson ice shelf is a pretty nice system because it sits on a so-called prograde slope, which is a very stable system. And so what we really see is only the response to the oceanic forcing. Where we are on an unstable system, then once you go into an unstable phase, obviously what you then tend to see is the dynamic response to the initial anomaly and not the response to the actual forcing that continues to move on. So here, what actually showing in gray. So during all of this period in red, was a period of retreat. So the grounding line was retreating, and the ice flow was accelerating in blue. And then when the heat flux decreased and the melt decreased, we then entered a period of re-advance of the grounding line. Another thing that's interesting to note here is the nice nonlinear connection between the heat content and the melt. And so these curves in dashed are the theoretical curves. So when there's no heat content, there's no melt. And then there's this initial sector where a little bit of change in the heat content doesn't lead to a large change in melt. But when we go into this regime, a small change in heat content leads to a very large variability in melt. So we have this power law linking the two, making the ice response, or at least the melt, pretty sensitive to heat content. How am I doing in terms of time?
I believe you should have a couple more minutes before we get to.
A couple more minutes. Yep. So I just wanted to very quickly show you the result of a very, very cool project that I've been leading with colleagues here at the University of Washington. So to explore these remote settings and to explore the cavities beneath the ice shelf, it's actually very difficult, very hard to reach. And so the state of the art still today has been the autonomous submarines, the AutoSub-3. So in 2009, 2014, we launched AutoSub-3 under the Pan ice shelf cavity, and it went, did an amazing job, completely autonomous, went all the way to the grounding line, mapped a few hundreds of kilometers worth of observations, amazing data. And it gives us, nice views of how the ocean heat content available in front of the ice connects to the back of the cavity. But of course, this is limited to in times to the order of a few days because it's a very expensive AUV, and we don't want to lose it. So we have to go there with a ship, and then we have to launch it and wait for it to come back and then retrieve it. So we have observations within a few days. We also don't want to get too close to the ice boundary layer because the ice ocean boundary layer because it's a very expensive toy and we don't want to lose it. So in the ocean, what we have been using extensively over the past decade are these wonderful other little tiny robots which have a much larger endurance, and they are the sea gliders and the floats. So I went to collaborate with Craig Lee's group, who are the leaders of sea glider development, and James Geerton, the University of Washington Applied Physics Lab, to use these floats and glider and try to deploy them for a full year under an ice shelf. And these are great because they can just be deployed in front of the ice shelf, and then we can leave and hopefully come back to retrieve them. But they are not as expensive, for one, and two, we can retrieve the data even if we're not around, right? They telemeter the data whenever there's open water. So for navigation, what we use are acoustic beacons that we place just in front of the ice. And then the glider, obviously, we can direct to go in and out. And the floats, they drift with the current, but we can decide to park them where we know that the water is inflowing, and they profile every so often. And at some point, we tell them, okay, now that you've been in this cavity for about 15 days, I want you to come back out, and to do that, I want you to track the base of the ice. And we did just that, and it's a very successful experiment, just came out. So last year, I went with Jason Gobat on the Aran Korean icebreaker, and we deployed 3 gliders and 4 floats in front of the Dodson ice shelf. And here is a map of all of the observations that were made, covering 14 months of observations. We extensive observations beneath the floating ice, The floats went in and out following the circulation that we expected. There's also a very nice little float that we thought we had lost, which actually didn't do as expected, actually found a connection, an unexpected deep connection between this cavity and another cavity on the other side in the back of the cavity right here. And I don't think I have much more time, so I don't want to bore you with the results. But suffice to say that it's a very interesting data set that puts a lot of perspective on everything we thought we knew about this system. I think I end here and open the floor for questions. Thank you very much.
Thank you, Pierre. So I guess it's time for questions or answers. As a reminder, use the raise your hand feature in the Ready Talk, and I will take you off mute to ask your questions, or you can also type it in the chat box, and I will ask it for you. So it looks like we have a question from Shane. Go ahead, Shane.
Thank you, Pierre, very much for your talk. Very interesting on many levels. In the first part of your talk, you describe your results with respect to El Nino or ENSO index. But I'm surprised you didn't talk about at all of the southern annular mode. You didn't see any influence of that index on your results?
The answer is none. But so the southern annular mode and the ENSO they are connected to one another, right? So that's one answer. The other part is the southern annular mode is very much a circumantarctic index, and it basically does not have a large expression on the variability of the Amundsen sea itself. I'm sure it has a lot of expression on a lot of other dynamics around Antarctica, but really this area has almost no correlation at all with the southern annular mode.
I see.
Yeah.
Thank you.
Yeah.
Any other questions for Pierre? All right. So if that's it, if there are no additional questions, thank you, Pierre, and thank you for everyone who participated today. We really appreciate you taking the time and informing everyone about your research. And as a reminder, we will have a posting of your presentation on the U.S. CLIVAR YouTube channel by early next week, so stay tuned for it. So thank you, everyone, for participating. Our next PAUSE panel webinar is tentatively planned for May 2nd at the same time. We also have an AMOC webinar scheduled for April 18th regarding ocean variability between models and observations that may be of interest to you all. So thank you again for participating.